Hello there. Welcome back to Chemistry Chem 131 at Southern Maine Community College. This is Chemistry for Engineers with Jennifer Termel, Chapter 5. And today we will be looking at gases, gas laws, gas velocity, kinetic molecular theory, etc., etc. Okay, so first of all, let's take a look at a few things here. Let's discuss the properties of gases. Gases expand to fill the volume of any container. Okay, that means that the volume of gases is not set. Uh, okay, so the volume is not set, it changes. Okay, so if something changes, it is variable. Okay, gases have much lower densities than solids or liquids. So solids, remember, have densities in grams per centimeter cubed, and liquids have densities in grams per milliliter. But gases, and I'll go ahead and change colors so it's a little easier to see here. Gases have densities in grams per liter because it doesn't make sense to talk about grams per milliliter. So we'll be talking about grams per liter here. Okay. And they have variable densities. And that's because remember, density is mass over volume. And so because our volume isn't set, our variable is all our the variable for density is also not set. And it's always going to depend on the temperature, pressure, and volume of the container we're looking at. And this is a very important thing here. Temperature will always be in kelvins when we're talking about gases. Pressure will be in a variety of different things. There will be millimeters of mercury, torr, pascals, but a lot of times pressure will be in something called ATMs or atmospheric pressure, and volume is going to be in liters. So we're going to need to convert to those. The next thing here is that gases mix with one another readily and thoroughly. And that change in volume is dramatic with the change in temperature. And that'll be one of the big gas laws that we're looking at. Okay, so let's go ahead and begin with the ideal gas law. The ideal gas law describes the relationship between temperature, pressure, and volume. Okay, and again, just like what I had mentioned before, your temperature must be in kelvins. For most of this chapter, we will be dealing with an R value that is a constant, and that constant is going to be 0.08206. And it's a little hard to understand these units. You can write them like this, 0.08206, and that's liter, atmosphere, mole, Kelvin. At the very end, we'll be looking at a second R value that's joules per mole Kelvin. And so that one will be a little bit different, but this is liter atmosphere per mole Kelvin. Whenever we're working with that ideal gas law, again, we'll need to do pressure in atmospheres. Volume will always be in liters and N for number of moles. So let's just review a couple of small things here. First of all, for volume, let's remember our volume conversions. Okay, and remember that there are 1,000 milliliters in 1 liter. And remember that 1 milliliter is the same as 1 cubic centimeter. Okay, and now on a different note, let's take a look at this N for number of moles. Okay, now when we're talking about number of moles, remember that you might be given a value in grams, and so we need to be able to convert from that. So to be able to go from grams to moles, you will need to take your gram value and set it up here to convert. And what goes on the bottom here is the molar mass of your gas. So don't forget how to do that. And then if we're going back from moles to grams, then what we'll need to remember is we'll have a certain number of moles. And we will multiply that by the molar mass grams per 1 mole. Okay, so that's just some review from before. All right. And you know what? I just remembered that sometimes these don't show you easily what your slide number is. So I'll go ahead and keep track of that up here again. This is slide 4. All right, now let's take a look at pressure. Pressure results from molecular collisions or particle collisions. Sometimes we'll be dealing with something that's not an actual molecule, like helium or neon or noble gases. So results from the particle collisions between gas molecules or gas particles and the container walls, as well as things within the container. Okay. The SI unit of pressure is actually the Pascal, but the Pascal is very, very small. So what they did is they said, okay, the average pressure at sea level is 1 atmosphere or 1 ATM. All right, now let's take a look at converting that. So first of all, if we are looking at the atmosphere conversion in here, okay, 1 atmosphere is the same as 760 millimeters of mercury or 101,325 pascals. Now, the millimeters of mercury or the torr, it's the same thing, comes from the height of a barometer. So back in the day, they used to have a barometer, and it was a long tube with full of vacuum placed inside a container of mercury. And the average pressure at sea level would give you a column of mercury that was 760 millimeters high. And so that 760 millimeters of mercury they decided to call that 1 ATM or 1 atmosphere to normalize it. And it is the average pressure at sea level. Now, if we're converting back and forth, we know that 1 torr is equal to 1 millimeter of mercury. Here's our primary conversion. And then just that there are 1,000 pascals in 1 kilopascal. Okay, so let's go ahead and take a look at the conversion down here. And this should hopefully be a fairly simple conversion. We have 2.67 atmospheres, and we want to convert that to millimeters of mercury, torrs, pascals, and kilopascals so that we can see what each one of those is. Okay, so first of all, we have our 2.67 ATMs. And first, we will go to millimeters of mercury, and we know that there is 1 atmosphere for every 760 millimeters of mercury. Okay, now this is exact. It looks like 2 sig figs, but it's not. It's considered an exact conversion. So we'll be going off of the 3 sig figs that we have right here. Okay, and when we work through this on the calculator, we will get 2,029.2 millimeters of mercury. Okay. Now, in our significant figures, because we can only have 3 significant figures, that would be 2,030 millimeters of mercury. And because a torr and a millimeter of mercury are exactly the same thing, then that would be 2,029.2 torrs for Torricelli, the fellow that did all that work with a barometer, or with significant figures, 2,030 torr. Okay. Now let's go ahead and find this value for pascals and kilopascals. So we start again with our 2.67 atmospheres. And every atmosphere contains 101,325 pascals. And the value that we're going to get then for our pascals is 270,538 pascals. So with our 3 significant figures, this becomes 271,000 pascals. And then if we were going to convert that value to kilopascals, we would note that there are 1,000 pascals in every kPa. Okay, which would give us 270.538 kilopascals. or with significant figures, 271 kilopascals. So hopefully that is all a review mostly from chapter 1, but there will be a lot of conversions again in this chapter. And this is a good time for me to remind you that if you were in class, I would be pausing after setting everything up and waiting for you to do the calculations yourself. So that is what you should do as well. You don't have to pause the video, but after I work through it, pause the video, put it through in your calculator, and make sure that you are getting the same answer. It's very easy for students to kind of have forgotten how to put their work into scientific notation on their calculators. Also, make sure that you're doing that with the calculator that you will be using in class, not with your phone calculator, because phone calculators work differently often than the calculator that you are using in class and for your tests. Okay, so we are up to slide 5 here. There we go. And we're looking at Charles's law. Okay, so now what we're going to do is we're going to look at a series of gas laws. And Charles's law says that volume and temperature are proportional. So that means that as temperature increases, volume will increase. And usually the temperature is what we're controlling. And so that is our X value, our independent variable, and volume is a thing that varies in terms of temperature, which is why that's on our y-axis, or our independent variable. Okay, now the thing to remember for all of this is that we have to be in kelvins. We cannot do anything in our in Celsius. So remember that kelvins are equal to our degrees Celsius plus 273.5. And the review for that is 0 Kelvin is called absolute zero. It's that point where we cannot get colder. And here you can see that the volume increases with temperature more strongly depending on our size. So our smallest molecule up here, helium, increases its volume with temperature very quickly. So there's a little bit of that going on as well. The equation for that is V1 over T1 is equal to V2 over T2. Okay. And you'll be solving for any of those variables. We'll be working through the actual math for this later. Okay. So our next slide here is for Boyle's law. And Boyle's law, this is our slide 6, just to kind of keep track of that. In Boyle's law, temperature and number of moles are constant. Okay, that's what's not changing, and pressure and volume are inversely proportional. So that means that if pressure increases, volume decreases, and also if pressure decreases, volume increases. And the equation for that is P1V1 is equal to P2V2. We will be doing a Boyle's Law lab in class where we will be able to see this curve that looks like an inverse exponential curve. Okay, and the important thing here is that these can be in any units as long as they agree. So your volume can be in milliliters or in liters. Your pressure can be in atmospheres, pascals, millimeters of mercury, as long as they agree. So don't feel like you have to convert to do Boyle's law. All right, our next law here is Avogadro's law, and that is our slide 7. And oh, sorry, there we go. Okay, sorry. In Avogadro's law, fixed pressure and temperature, the volume and number of moles of gas are directly proportional. Okay, so N is number of moles, just like we had mentioned before, and we have to convert our grams to moles for this. V is volume, and it can be in any units as long as they agree for Avogadro's law. And just a little review for how this works. Let's review using something called the Haber process, which is how we make ammonia commercially from nitrogen and oxygen. So if we have nitrogen gas and hydrogen gas, we will make ammonia, and that's also a gas. And when we balance this, we have N2 here, so we can put a 2 here. And now we have 6 hydrogens, so we'll put a 3 there. And so what we're looking at right here is that we're looking at, we have 1 unit of N2 is going to be attached to 3 units of our H2. And you can see that here we have 4 units of volume because we have 4 moles. And that's what that means with that proportionality. And then on this side, we have just 2 units of NH3. So what this will form is that during this, we'll go from having 4 units of volume to only 2 units of volume. And that is because our volume for a gas is mostly empty space, just reviewing back to chapters 1 and 2, mostly empty space. And it doesn't matter how large the molecules are, just how many we have of them. All right, so let's go ahead and start working on some practice problems. Okay, so our first practice problem here is slide 8. And it tells us that a common laboratory cylinder of methane has a volume of 49 liters and a pressure of 154 atmospheres. Now, what we're going to do is we're going to suppose that all of the CH4 from this cylinder is released and expands until its pressure falls to 1 atmosphere. And we want to know what volume would CH4 occupy. So what we do is we start by saying, okay, so what is changing? What is changing is volume and pressure. And Gauss's law tells us that things are changing for volume and pressure is Boyle's law. And that is P1 V1 equal to P2 V2. Okay, so now the first thing to do here is to say, okay, well, our initial pressure is 154 atmospheres. And our initial volume is 49.0 liters. And our final pressure is 1 atmosphere. And our final volume is what we're looking for. So we can set up our math here. Then we have 154 times 49.0 is equal to 1.0 times V2. And just to solve for V2, then we would have 154 times 49 divided by 1. And that will give us 7,546 liters. Okay, I can only have 3 significant figures, so this becomes 7,550 liters for our final answer with our 3 significant figures. So now we are up to slide 9, and we have another practice problem here. Here we have a balloon filled with helium, and its volume is 2.2 liters at a temperature of 298 kelvins. The balloon is dunked into a thermos bottle containing liquid nitrogen. When the helium in the balloon is cooled to the temperature of the liquid nitrogen at 77 kelvins, what will the volume of the balloon be? Okay, so now what we have is we have volume and temperature are changing. And if volume and temperature are changing, that means that we are using Charles's law, which gives us V1 over T1 equal to V2 over T2. And so we make our list. Our V1 is 2.2 liters. And our T1 is 298 kelvins. We're already in kelvins, so we don't have to convert. Our V2 is what we're searching for. And our T2, our final temperature, is 77 kelvins. So now we're going to set this up, and we have 2.2 for our V1 over 298 is equal to V2 over 77. And just as a little review here, if we can solve this through cross multiplication like that, and that means that our V2 value will be 2.2 times 77 divided by 298. And the value that we will get for that is 0.568456. And our unit is liters. Now notice over here that we can only have two significant figures in both of these places. So that means that with significant figures, this is going to be 0.57 liters. Let's take a look at another one. This is starting to get into some larger, more complicated ones. Okay, so this is slide 10. And I here have a bunch of steps for you to use. So first of all, we have a sample of ethane, C2H6 gas, and it has a volume of 546 centimeters cubed. We have a pressure of 752 torr, and we are at 77.6 degrees Fahrenheit. Okay, and we want to know what mass of ethane is in the sample. So our first thing here is it says, what law do we use? Okay, so first of all, nothing is changing. So that means that we're going to be using the ideal gas law. And the ideal gas law, remember, is PV equals nRT. All right, now step 2 here tells us to convert to liters. So remember that a centimeter cubed is the same as a milliliter. So we have 546 milliliters, and our conversion, we have our milliliters on the bottom and liters on the top, will give us 0.546 liters. And that is our volume. All right, and our next step here is to convert our pressure to atmospheres. And here you see the torr. So we'll go ahead and say, okay, 752 torr times, okay, now we finished this conversion here, and we have 760 torr on the bottom and atmospheres on the top, which we can have three significant figures. So this becomes 0.989 atmospheres. And now we need to convert our temperature to kelvins, and this is going to be a little bit of a longer process. So just as a review from chapter 1, and also this is on the back of your periodic table with your ion list, but we have to convert from Fahrenheit to Celsius, and we are currently in Fahrenheit, so let's go to Celsius. Okay, so degrees Celsius equals our degrees Fahrenheit minus 32 divided by 1.8. Okay, so you see 9/5 or 5/9 instead. Either one is exactly the same value. 9/5 is the same thing as 1.8. It's just that when you're typing things into a calculator, dividing by 1.8 is a little bit easier than dividing by 9/5. Oh, so what this will give us now, notice here, so here we have 77.6 Fahrenheit minus 32, which is exact, divided by 1.8. So we only have three significant figures here. And so what we'll end up getting is 25.3 degrees Celsius, okay, plus 273.15, which will give us 298.45. Okay. And that will round us to 298.4 kelvins because we've got that first bit here. And if you wanted to go even farther, that would be 25.33, just so you know, which actually gives you an 8 there. So you can see you're definitely going to round up. So here we go. Here is our Kelvin temperature. Oh, sorry, 294. Look, I said round up and then I didn't round up. Okay, there we go. 298.5. Good. Okay. Now what we're going to do is we're going to solve for moles using your gas law. Okay, so if we have PV equals nRT and we need to solve for N, that becomes N is equal to PV over RT. Going to actually use that a fair amount. Okay. Okay, so then I'll go ahead and change color so that everything is kept separate. Our pressure right here is 0.989 times our volume, which we have up at the top, 0.546, divided by our R value, which never changes, 0.08206, times our temperature value here, 298.5. I'm with parentheses around each top and bottom because some calculators, if you don't have parentheses around the bottom, it will not give you the correct answer when you're dividing. So I've gone ahead and put that in there like that to show that. Okay. And so we have 0.989 times 0.546. And now we're dividing it by our bottom, 0.08206 and 298.5. And what we get here is 0.22045515. And we can only have three significant figures, 1, 2, 3. So we want to remember how we're doing that. Okay. And so that becomes 0.220. And here our units are in moles. Now we have to convert to grams. This is a very long and challenging problem. So this is going to become our new given 0.220 moles. Okay. And remember, we're going to need a molar mass. So just as a little review here, we have C2H6, so that's 2 carbons and 6 hydrogens. Okay, so 2 times 12.011. I got an extra 1 in there. That's not what I want. And 6 times 1.008, which gives me a molar mass of, we got 12.011 times 2 plus 6 times 1.008, and it comes to 30.070, and that's grams of ethane per mole. Okay. And now I can have three significant figures for my final answer, and that gives me 0.662 grams of ethane. And that is my final answer. So all of that work just to get this value at the bottom. Let's take a look at partial pressure. Partial pressure is basically talking about how gases, oh, and sorry, this is slide 11. There you go. Air is a mixture of different gases. We know that. So air itself is mostly nitrogen with some oxygen and tiny bits of water vapor, carbon dioxide, all kinds of other things tossed in. Gas laws do not depend on the identity of the gas because the pressure is due entirely to the number of moles of gas present, because that's what volume is due to. Excuse me. The pressure exerted by a component of a gas mixture is called the partial pressure of the component gas. Okay. So Dalton's law of partial pressure tells us that the total pressure of a mixture of gases is the sum of the partial pressure of the component gases. So what that means is that we can add this up. And so our total pressure is equal to the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3 and so on and so forth. And that's kind of how we find that. Okay, so now we look at what we'll use before we can get there. So first of all, Dalton's law can be expressed also in terms of a mole fraction. A mole fraction has no units, and it's always going to be a decimal. Okay, and it's the moles of gas A over the total moles. We can also say that the pressure of gas A is equal to the mole fraction of A times the total pressure. Okay. And let's see. And that's another way of kind of working through that. Sometimes you'll also use that the total pressure is equal to the pressure of A divided by its mole fraction. Let's go ahead and take a look at a couple of problems here. Here we are on slide 13. And let's take a look at this. So first of all, we have 5.26 moles of hydrogen. Okay, so that's 5.26 moles of H2, just to remember. And then we have over here, we have our 8.34 moles of helium. So that gives us 8.34 moles of helium gas. Okay. And we have a total pressure of 1.15 atmospheres. So this is P total. Okay. And we want to know what the partial pressure of each gas is. Okay. So for this, our step one is going to be to find total moles. And so we'd say, okay, well, the total moles of our stuff is 5.26 plus 8.34, which gives us 13.6 moles total. Okay. And we know that our P total is 1.15. So the next thing that I'm going to do here is I'm going to find our mole fraction for hydrogen and for helium. So let's go ahead and we'll go here and we'll put hydrogen over on this side and we'll put helium over on this side. And we'll say, okay, that the mole fraction of our hydrogen then is equal to 5.26 moles divided by, not divided by the other one. Hang on, let me erase that. Divided by our total of 13.6. And that gives this a mole fraction with three significant figures of 0.387. And now we can come over here and we can find the mole fraction of our helium. And that's going to be the moles of our helium, 8.34, divided by our total of 13.6. And so with three significant figures, the mole fraction of our helium is 6.13. Now pause for a moment and notice that 0.387 and 0.613 add for 1. So your mole fractions will always add for 1. Now what we can do is we can calculate our partial pressures. So the partial pressure of our hydrogen is equal to its mole fraction, 0.387, times the total pressure, 1.15. And that is going to give us 0.445 atmospheres for our hydrogen. And then the partial pressure of our helium gas is the mole fraction of our helium times 1.15. And that's going to give us a partial pressure for helium of 0.705 atmospheres. And again, in this case, you can notice that 0.445 atmospheres and 0.705 atmospheres will add for your pressure of 1.15, which is Dalton's law in a nutshell. Okay, now we have our next slide here. And this slide is going to be, I have to figure out where I am here. Here we go. We are on slide 14. Okay. All right. Now let's take a look at our steps. On your paper, you have your steps printed out. I don't have them on the slide because I need space to work and I only have this small space here. Okay. So a scientist trying to generate a mixture of gases similar to that of volcanic gases. We have 15 grams of water vapor, 3.5 grams of sulfur dioxide, and 1 gram of carbon dioxide, all mixed into a 40-liter vessel and held at 120 degrees Celsius. We need to calculate the partial pressure of each gas and the total pressure. Okay. So looking at your steps there, your step 1 is to find the molar mass and the number of moles of each gas. Okay, so I'm going to find the molar mass while I'm working through this. So first of all, we have 15 grams of water. And at this point, you should probably be pretty good at this. So our molar mass of water is 18.015 grams per mole. Which gives us a water value of 0.833 moles of H2O. And I'm going to actually color code these values here. Okay. And our next one, ooh, that should have been in green. Okay, that's okay. And then for our sulfur dioxide, we have 3.5 grams of sulfur dioxide. Okay. And our molar mass of sulfur dioxide is 64.058. And that will give me a number of moles of 0.0546 moles of SO2, sulfur dioxide. Okay. And last but not least here, we have our 1 gram here of our carbon dioxide. And so 1 gram of CO2, and the molar mass of CO2 is 44.009 grams per mole. That will give us a number of moles of CO2 of 0.0227. Okay. Now our step 2 on your sheet here is to convert our temperature. So let's actually we're going to come up here and do step 2, and we'll say, okay, well, we take our 120.0 plus 273.15, which will give us 393.15 kelvins for our temperature conversion. Okay, and now let's go ahead and go on to step 3. And there's actually a couple of ways of doing this. So let's go ahead and work from here. Our step 3, though, to stick with this, is to use the ideal gas law to solve for pressure. Okay, so if PV equals nRT, then pressure is equal to nRT over volume. Okay. And for each gas, then, for our pressure of H2O, that will give us 0.833 times 0.08206 times 393.15 divided by 40 liters, which is going to give us a pressure of water of 0.672 atmospheres. And then we're going to find the pressure of our SO2, and we're going to use that number of moles. So then we have 0.0546 times 0.08206 times 393.15 divided by 40. So a lot of this is going to be exactly the same for each one. And that will give us, in these, we only have 2 significant figures for these last ones. So that'll give us 0.044 atmospheres. And that's for our SO2. And I'll clarify that this one here is for our H2O. And then last but not least, we have our carbon dioxide and, sorry. And the pressure of our carbon dioxide then is equal to that number of moles, 0.0227 times 0.08206 times 393.15 divided by 40 liters. And that will give us a partial pressure of CO2 of 0.018. And that's atmospheres of CO2. Okay, now your very last step here, step 4, is to use Dalton's law to solve for your total. And remember, so that's going to be P total is equal to the pressure of H2O plus the pressure of sulfur dioxide plus the pressure of carbon dioxide. Okay, so that's 0.672 plus 0.044 plus 0.018, which will give us an overall of 0.734 atmospheres for our total pressure. I think it's a great place to go ahead and take a break. We will come back and we will finish chapter 5 in our part 2 video.